We've mentioned divergence and curl before. Now we want to take a specific look at computations of divergence and curl and their applications. And we've worked with the two-dimensional quantity before that is representative of divergence. The three-dimensional version of divergence is very much like that. We just add the derivative of the third component. Now, this measures the flux through a surface. We'll see that in the very near future. Now, we've worked with the quantity also given by the partial of g with respect to x minus the partial of f with respect to y when we were doing Green's theorem. And the three-dimensional version of that is a little bit more complicated. Now, I don't know if you recognize the pattern of partial derivatives here, but we'll be taking a look at that here in just a moment. Now, this measures the rotation of a vector field. Now, let me show you how we use this symbol, which is called the del operator. Now, this is an operator, so here's kind of how we use that. Del represents the vector comprised of these incomplete partial derivatives. Notice here we've got a partial symbol, but nothing beside it. Now, again, this is what the meaning of the del operator is. So, when we combine the del operator with something, it's a very similar situation to multiplication. So, we're basically taking the del vector that we have up here and putting a g with each component. So, the del g is actually the vector that we get when we do the partial of g with respect to x, the partial of g with respect to y, and the partial of g with respect to z. So in that sense, the del is something that operates on the g doing its partials. Here's another one where del is operating on the f. Now, if you look at this one, if we take the del and do the dot product with f, here I've got that laid out, del dot f, this is not technically a multiplication. We're not taking this first component and this first component and multiplying them in the sense of the dot product, meaning multiply. But we are putting those together, and as you can see, it comes out to be the partial derivative of f with respect to x. Now, if all of this looks familiar, that's because I just had it on the screen a minute ago, and we're going to take a look at it again here in just a moment. So then, if we take a vector field given as f, g, h, the divergence of f, which we write as div capital F, is the dot product of del and f, which we just had on the screen. That's our formula for the divergence of the vector field. Now here, if we do the cross product of del and f, here's my del, here's my f, here's the I, j's, and k's that we use. So we're going to do the cross product. Now when we do the cross product, we'll go this direction, this direction. Let me remind you that here on the I, we were taking this and this. The cross product actually says we're multiplying those. But when we put them together, we come out with this. Now again, technically that's not multiplication, but we're putting them together in what looks like multiplication. This comes out the derivative of h with respect to y, and so on. And that is our definition for the cross product of the curl of f. Now this is pretty easy to remember. Look at the highlight. The divergence is a scalar quantity, and it's the dot product. Notice the d's. The curl is a vector quantity, and it's the cross product. Notice the c's. So again, this is pretty easy to remember. Let me remind you that you can get the curl of a two-dimensional vector field by inserting a third component so that you can do a cross product. So the divergence measures how much we are expanding at each point in a vector field. If the divergence is 0, we call the vector field source free. Here's the divergence. So here's the computation of divergence for the vector field x, y, z. Partial of x is 1, partial of y is 1, partial of z is 1, so 1 plus 1 plus 1 comes out to be a 3. Here's the computation for divergence of this vector field. And here's the computation of divergence for this vector field. Now, the quantities themselves aren't of a lot of value unless we have some place to use them. For example, notice here in the middle, this vector field is source free. Okay? This vector field is more divergent than this vector field. There's more going on, there's more expansion in the first vector field than in the third one, and there's not any in the middle one. But again, it's a comparative number. So anyway, that's the measure of divergence for those three. Well, let's measure the curl for those three. Now, the curl measures the rotation. The first component, the I component, measures the rotation around the x-axis. The J component measures the tendency to rotate around the y-axis, and the K component measures the tendency to rotate around the z-axis. So, here's the formula for curl. Here's the same vector fields that we were just measuring. So, if we do all those derivatives, and I'm not going to take time to manually do each one, but they're pretty easy to do. For example, in this first computation here, remember these are M, N, and P. So if we do the derivative of P with respect to Y, that's the derivative of Z with respect to Y. Well, that's a 0. The derivative of N, that's this, with respect to Z, is also 0. So we come up with a curl of 0, 0, 0, or the 0 vector. The second one, the curl comes out to be -1, -1, and 1. The third one, 0, 0, and 2. Again, the numbers in themselves aren't of that use, except for maybe the first one. Notice this is an irrotational vector field. There's no rotation in this vector field. This vector field, however, has rotation in every direction. This vector field has rotation in only one direction. Now here are the graphs of the three vector fields. Now, I don't know if static graphs help much. You can always go to Maple yourself and draw the vector field of each of these in Maple, which is what these images are, and then manipulate it so you can look at it from different angles. However, again, notice in this first one, we've got a divergence of 3. So we've got a positive divergence. Look at the vectors. They're all emanating out from the origin. So a lot of divergence in that, but no circulation, no rotation. The second one has what? No divergence. These vectors are going every which way. So there's lots of vectors going in all sorts of directions, but not a lot that's actually going out in any one particular direction or in any one particular direction. They're rotating in all directions. And as you can see, that is technically called a rotational field. And in the last one, we have one that has a little bit of divergence and a little bit of rotation in one direction. Now that's rotating around the z-axis. You can see that clearly right here where z equals 0. You can see all of the vectors going in a circular fashion there. So let's take a vector field and actually do the computation for divergence and curl. So have the formulas handy, or better yet, program them into your TI-89, and let's do the divergence and curl. We'll call these F, G, and H for use in the formula. So here's our formulas for divergence and curl. We do, for divergence, the partial of the first component with respect to x, partial of the second with respect to y, partial of the third with respect to z, and then add all of those up. Notice that we come up with 2xy plus xz, which is not 0, meaning this is not source free. So let's measure the curl of this vector field. Here's the partial of h with respect to y. We're going through the formula. We'll do g with respect to z. We'll do f with respect to z. We'll do h with respect to x. You get the idea. We're just going through the formula. And then we put all those together. Notice that we do not come out with the 0 vector. Therefore, this is not a conservative vector field.